The William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank the U.S. DOT for their ongoing support. It is greatly appreciated by those of us here on campus, as well as those participating via the internet. And let me welcome those of you who are participating via the internet today. We have representatives from Quandel, Benesh, Rail Sciences, Patriot Rail, First Solar, LTK Engineering, Benesh, Amtrak, Hatchmont McDonald, Lochner, Metra, Federal Route Administration, Parsons, Hanson Professional Services, and Trans Systems. And again, those of you who are dialing in, if you would like to receive PDH credits for your participation, please send Emma an email with your information. And now to introduce our speaker, let me introduce my colleague, friend, and the leader of the Transportation Engineering Group, Errol Tutumler.
Thank you, Chris. It's indeed a pleasure for me today to introduce Dr. Guoqing Jing. First, let me read his abstract to you. His abstract goes like, ballast flight occurs when very high-speed trains pass over ballasted track, ballast particles become airborne. The potential for damage and injuries from these high-velocity pieces of ballast has raised concerns regarding use of ballasted track on high-speed rail lines. Our speaker today will discuss why, when, and how it occurs, the risk it poses, and under what conditions. He has conducted extensive research using innovative methods to understand the phenomenon and reduced the ballast flight risk, including ballast bed design and optimization, polyurethane application, and use of aerodynamic crosstie designs. Guoqing Jing is an assistant professor at Beijing Jiaotong University and is currently a visiting scholar at the University of Illinois at Urbana-Champaign with my research group. Dr. Jing completed his PhD research on high-speed ballasted track at the Institut National des Sciences Appliquées de Rennes, that's in French, of course, and in France in 2009. That was my broken French. His research interests and expertise include testing, modeling, and innovative structure of ballasted track, high-speed railway ballast flight, and counteractive methods. He has served as an investigator on more than a dozen research projects with major railroad grants received from National Natural Science Foundation of China and the China Railway Engineering Corporation. Dr. Jing is also a member of the China Railway Standard Committee and a reviewer of the National Natural Science Foundation of China. He has served or is serving as an invited senior consultant for the Iran high-speed rail project, the Russian high-speed rail project, and worked as chief railway engineering consultant for the Mexican high-speed rail project. So with that, please join me in welcoming our speaker today, Dr. Guoqing Jing, who will present the William Hay Seminar, a railroad engineering seminar, entitled High-Speed Rail Ballast Flight and Measures. Dr. Jing?
Thanks, Chris. Thanks, Errol. And thanks, Bodini comes from long distance. And my name is Jing. And I'm working for ballast track more than 10 years. Even I look young, but I have been working for 10 years. I'm honored to share my research and work with RUTEC and colleagues and students. And this is my second dream when I'm working as a visiting scholar here. Now, next, this is my outline. First, background and the research progress. And next is experience in China. And my future development, innovative method for higher speed, for example, 400 kilometers per hour. My research topics, first one is high-speed railroad ballast flight, higher speed. This is my primary topic. I got 3 foundation research funds from National Science Foundation of China. And next one is modern ballast track structure, like I call it composite structure, or the modern railway track. Use under-sleeper pad, ballast mat, geogrid, polyurethane, and even other materials, rubber system, asphalt layers. Next part is traditional ballast bed mechanics and application, like the interaction of ballast and railroad tie. I'm a small and young version of aerotutomer. Just remember that enough, okay? Next one, I show you a global perspective of China high-speed railroad network. Up to now, we covered 20,000 kilometers of high-speed railroad, about 12,000 miles miles. And not only we cover 2/3 of the world high-speed railroad. More than 10 years ago, we have nothing. In just decades years, we from nothing to the number one and far beyond the second position. And not only the total mileage, but also, for example, here, west, desert land, northwest, northeast, cold zone. And here, we have the run, high-speed run in this island, on this island. And we even have the ambition and dream to connect with here, Taiwan. If political allows possibility, we can construct underground by the tunnel, no problem. And another thing to share with you is that, for example, from Jinan here, from Jinan to Qingdao province, from Jinan to Qingdao, just within Shandong province, we have 3 railway lines: freight one, high speed one, 250 km per hour. And now we are constructing the third one, 350 km per hour, just within connect the 2 cities within 1 province. All wanted to show you that from nothing, we cover a big, remarkable goal. Next one, 90% of China high-speed railroad, we use slab track. It is pity for me because not only because of the money, we invest too much money, but also consume too much cement, steel, and pollution. Too much. And this is not, somebody will ask maybe, why use slab track, why use ballast track? This is not subject of today. But I want to say that each country, each product, the LCC, life cycle cost analysis is different. And even for the same country, same product, 10 years ago, for example, from Beijing to Tianjin, the first high-speed railroad in China, the slab track, we use this one. 10 years ago, each unit block, 6 meters long, cost more about $4,000. But now, each block costs just $1,000. Because we have large scale, we can cut down the unit price. But for some country, you could not benefit from this technology or the market. When I share my lessons with my local students, I will use the analogy method. I compare the slab track to men. Strong, rigid, sometimes stubborn or stupid. And the ballast track is like female. Flexible, gender, smart. Yes, this is it. Yes. And each coin has 2 sides. The ballast track advantage is the disadvantage of slab track. Remember that is enough. Next one. Just as the last seminar, David Lange said, micro cracks is the nature of concrete, born with nature. We could not change it. And with time of service, ballast slab track have problems. Water, temperature, settlement. It's pity that 10 years ago we didn't realize this problem seriously. For example, the cracks control. We just design, control the quality of strength, but some kind of omit the cracks. Huge problem. And I could not present too much photos of like this, but we have lots of situations, conditions. It's very difficult to repair it. We need a curing time within the window time of 3 hours. Impossible. And even we use chemical reaction method, like polyurethane, but still have problem. Detection method, and evaluation, post-evaluation. But some small companies working on it. We hope help. I also use the analogy with my local students that slab track is like the traditional Russian female. For the first 20 years, pretty excellent. Yes, after another 20 years service time, just so. But maybe for the final stage of the last 20 years ago, you don't want to see her, don't see her at all. So this is my share with my local students because yes, when you visit on site, excellent. But with time in aging, the aging is not like this, but like this, okay? Oh, I want to share something very secret or important with you. Why we use slab track 10 years ago, more than 10 years ago? Because there was challenges, there was some kind of so-called reason. And now we have solutions. For example, about 12 years ago, when we first, after 6 times of speed up, we import the high-speed train from Japan, from European, to operate on our existing railroad lines. We have the problem dust drift. I will talk to you later. Dust, rubbish, dust flight. So the railway authority worry about ballast flight. And we hired SNCF from French, DB from Germany to give us consulting report for the high-speed railroad selection technology. And at that time, even French, they have little worry about ballast flight. Okay, this is more than 10 years ago. Next one is extra tough ballast resources, availability and reliability. Ballast is very cheap, but the transportation fees is huge if beyond some proper distance. And for some reason, some countries don't have this excellent ballast resources. For example, when we export our railroad in Africa, a stupid designer of China, they just recommend in the contract use grade 1, which is the normal strong ballast. But after subgrade finished, they found out there's no qualified rocks. So you must investigate if there is enough or within proper distance of the excellent ballast. Why? Because 10 years ago, more than 10 years ago, the China Railway Company, they control every unit price for construction. For example, low price. But now we open to the market. Higher price, more suppliers, excellent suppliers. So this problem solved. Next one, modern ballast track. When we talk about ballast track, everybody knows ballast track, sleeper, ties, ballast, nothing else. But with the evolution and the development, changed a lot. I also use analogy to share with you and the same with my local students. That ballast track is female, slab track is male, but between them there is we internally call it PhD female PhD. This is no offense. In fact, this is some kind of, we call it a female but very strong. This is the way I call it modern ballast track. Female in nature but very strong in structure. We call it modern ballast track. So like USP, PU, this is new technology. Next one is degradation and maintenance. When we talk about ballast track maintenance, somebody old-fashioned, old school will say short-term maintenance. But I asked her or him, do you know how much is it? Nobody gives the exact term. Something I share with you, for example, French. After the first high-speed railway road put into operation, the second generation, even higher speed, but the maintenance period prolonged. For some zone, almost doubled. This is because new technology of construction and maintenance. So this is why we use slab track. Next one, this is the old school of common ballast track, old tradition. But I want to say high-speed ballast track go far more than that. First, I want to make a declaration that the maximum speed for ballast track is almost 360 miles per hour. Number one for the high-speed train, far more than the slab track, French. Second, firstly, when we increase the speed, the cyclic frequency, dynamic frequency increase, the ballast granular become kind of gather fluid flowability. For example, the speed of 320 km per hour, almost the similar frequency for tamping. So we must use the dynamic design for the ballast track. Secondly, I want to share the development of the ballast high-speed track, high-speed railway. 3 generations, different speed, and different interesting topic. For example, 50 years ago, when the first high-speed railroad by the Japan, the speed just 200 km per hour. What they worried about is strength of the ballast-bed. And the second generation is French. About 30 years ago, when the speed is 300 km per hour, they worry about like the buckling, CWR stability, dynamic of effect. But for the last decades, the speed, for example, now French, the operation speed is 320 km per hour ballast track. After that, for the last decades, we worry about high-speed ballast flight. This is a very hot topic of research for the past 10 years. But the current challenge comes environmental, geological, and operation. For example, I'm now working for Russia project, Iran project for the high-speed railway design. For example, this one, Russia. I share with my fellows that Russia is very tricky or smart, too smart. They want everything. Different speed, 300, 350, 400, both slab track and ballast track. China have to share the technology, design, and so and the operation conditions very complex. Freeze and thaw, snow. So But we have no choice. We have to fulfill the job. Next one is Iran, desert and earthquake, political and even terrorist attack potential. So for this one, something I want to share with you, when the China high-speed railroad export, the authority, high authority, central government want to, everybody use slab track. Even we don't earn anything, even we lose money, we want to use slab track. Some kind of stupid. I told them not stick too much on slab track or the Chinese standards. Just use Chinese products enough. It is pity some countries we use our standard, but every product comes from local. So what's the difference? Standard. Okay, something I want to share with you. This is research interest in the future. Shared corridor. French, next year we finished. From Nîmes to Montpellier. Both freight and passenger. This, in fact, in my opinion, this is very good for most of the countries. Good enough, both. This is my third part, current challenges. So next one, okay, ballast migration or ballast dislocation. 10 years ago, or almost 8 years ago, a local chief engineer of the company, railway company, he asked me, Dr. Jing, why it is so difficult to keep the geometry of the ballast bed? Is it because of the dynamic effect? I told him that not only dynamic loads, but also aerodynamic. So UIC high-speed railroad report suggests that the geometry of the ballast bed should be weekly checked. Because this migration of ballast, okay, this one, migration of the ballast, accumulation somewhere, and dislocation somewhere. So stability of the track. For the higher accumulation part, easily result in ballast pickup. So the initial stage of the ballast flight, this one, next one, dust flight. This happened in China. More than 10 years ago, 2003, 2004, when we first imported the high-speed train, operate in our old tracks, we found that dust everywhere. So at that time, we were worried. We worried a lot. Ballast-flight. So, and there is also a joke shared with you that because we import the high-speed train from Japan air conditioner, the input is underneath, which means we breathe in the polluted, dirty things into the car. After we change, we modify it, change it. So this is our experience for speed up. Maybe for some country, if you import the high-speed train, operate in the existing line, dirty lines, maybe you will have this kind of problem. Our solutions, we add fresh ballast and cutting after 3 months to 6.5 years operation, no problem. This is delusion. Make a setback for us at that time. Next one is ballast flight in snow zone. I also consulting have the research product funding from the company. Snow accumulates into ice, and when the train, high-speed train, run from warmer, cold distance to the warmer zone, for example, Harbin to Dalian. So there is a temperature variation. And when the high-speed train into the station and out of station, temperature changed. And when the train transport, there are dynamic effect. For example, transition zone, bridges. So the ice metal, and sometimes fell down. This is like a bomb, high-speed bomb. Hit the ground and the ballast, or even on the slab track, because the ice turn into small pieces and will protection to the train. In our this is our experience. So in winter, we have to reduce the speed. Summer speed, winter. Japan, I should admit that Japan is the best of best for this operation and management technologies. We use de-icing operations for the train, snow removal machines, and we turn out heating system, high reliability systems, and the slow down method. This is the next one, Japan best. And now we talk about the true ballast flight. True ballast flight, usually the speed up to 300 km per hour. Somebody said 250. In fact, that rarely happens. If usually above 300, the ballast particle acquire enough momentum and will pick up due to the aerodynamic and dynamic force. Sometimes hit the train and also the tracks, and damage and even surrounding. By our inner report of China high-speed train company, each year, each train will need several thousand $US to repair the train. Very less, but need some repair, which means there's a ballast flight happen in China. Ballast flight mechanism and risk, very difficult to find out what is the reason, because lots of interdisciplinary, cross-discipline factors influence each other, interlocking. By the dynamic force, vibration, and the wind. So by Bedini, each factor influence each other. So it's very difficult to quantify exactly what is the reason, what is the contribution for the ballast flight. I will share something interesting test. This is Japan. They use the canoe, ice, 3 kilo weight, air pressure, different angle, and ballast, and both ballast and ice. Projection, camera recorded position and height. And French did similar research 10 years ago. And 10 years ago, Jing, SNCF, vibration, and also wind tunnel test. And Korea, KTX, they did this kind of test, wind tunnel test. But this one, I doubted the result because they just put the ballast particles onto the ground. By the perspective of the wind aerodynamic engineering, there is a frictional boundaries, the boundary effect. So different speed you have to heighten to the platform at an exact position. For example, my research, I made a table, put a ballast onto it. Side test. This is Ampleton, William Horry, like Chris Baker. They did the research of the ballast vibration and the ballast test pickup. But the speed is very slow, just 270 km per hour. So no ballast pickup. And Spanish, they are pioneer researcher for ballast flight. And next one, my research in practice. Theory, lab test, and practice. First one, just look at this one. We just, because this discussion is not the object today, Anybody interested can find me for details. I want to use a simplest way to quantify the ballast while flight. So use the force, equation, there is a gravity, interlock, wind force, and vibration. I use this one to set up equilibrium. And deduction and calculation, finally we can get this one. Very interesting, simple but interesting. For example, I found out there is this total vibration. We can find out the ballast flight correlates with the mass, density. Bigger density, less occurrence of the ballast pickup. And this ballast vibration. So we can find measures to reduce ballast-bed vibration. And also this one means the flight of the ballast ship. Very interesting. And also density, rho, which means density. For some reason, for example, volcano, production of ballast. The ballast particles very strong, but the density relatively very slow. So this kind of ballast easily pick up. Okay, next one. Okay, reliability. This is about, before is qualitative. Now we come to quantitative analysis. This is refers to Chris zone. So with my force equation, I can set up the function of the ballast pickup reliability analysis. Use different methods, we can have some kind of quantitative analysis result. Next one, our lab test. We use the different speed, different shape, size, and ballast. And we also fix ballast particles and drill a hole, put the pitot rope tester to test the surface pressure. We find out small particles easily start to move. And the next one, this is ongoing. I use the wood to build a platform, and then we add stick, bonding ballast, and another layer. Different ballast shape, size, and I even want to use 3D printing, same size, same shape, different size, and different density to test the possibility of ballast flight. This is wind tunnel test. And we also can test the wind pressure distribution, and together working with our safety. Computational fluid dynamics usually used, for example, by Chris Baker for the high-speed train, and somebody else used for the interaction with the tunnel to select the shape of the tunnel for the high-speed train. But I'm almost the first one to use the CFD for ballast-bed geometry optimization to find out how much and where and what is the distribution of the wind pressure. We find out here is vortex of ballast, wind. And we also research shoulder ballast. Shoulder ballast is vital to keep the ballast track stability. Different shape, different height influence. We use the CFD for evaluation. And we find that wind pressure increase a lot with the height increase. Next one. This is from ADIF, Spanish. Excellent. They use the CFD for optimization of the crosstie. It is said that by this aerodynamic sleeper tie, reduce 50% of the risk of ballast flight. Yeah, I don't know how to calculate. The basic said. Okay.
Could you go back one slide,
I'm curious, why does the shoulder ballast extend above the surface of the tie?
Excellent. Okay, I will show you this one to answer it.
If you're going to get there later, then we'll just wait.
Okay, this one. Okay. I have paper and by discrete element method research and field test, laboratory test. Ballast single sleeper resistance comes to three parts: bottom friction, shoulder ballast, shearing, and also the sleeper side friction. And different research gives a different result. For example, European tell that 40% comes from underneath, 35% comes from the shoulder ballast. And the shoulder ballast width and height is vital one, because provide the loads to keep the track. And I use this is my discrete element method research evaluation, because contribution and evolution, for some case, for example, uplift the track, lose contact of the bottom. For some other, we reduce the shoulder width, shoulder height, there's changes. Sometimes we have to reduce the crib ballast layer. So there is something like this. Okay. The ballast high-speed train, the slab track, the CWR stability is some kind of conflict with ballast flight. With the speed of increase, we have to provide more lateral resistance. The most efficient way is to heighten shoulder bigger. But the bigger shoulder ballast part result in much more occurrence of the ballast flight. This is the conflict. We have to make a compromise. The same thing also for this is one compromise, conflict. Speed increase, we have to lower down the crib ballast, but result in poor or reduction of the resistance. Okay, I hope it's okay for your question. Okay, so we'll next. Thank you. Next one. Okay, why this is efficient to reduce the possibility of ballast flight? Because it's very important. After construction or tamping maintenance, the ballast particles easily spread onto the top of the sleeper tie. Because the tie vibration is 10 times of the ballast bed. So by my equation, this is easily picked up. So each country have very strict rules of sweep off the ballast. If we use this shape wrongly, the ballast could not easily rest there. So this is not only because of the aerodynamic of the degradation, but also because of the geometry. The ballast could not stay there naturally. So this is our simulation. We use this one maybe for the future for the Russia high-speed railroad design. Next one, practice. This is a translate from our high-speed railway design codes and also effectively in China. First one, this I said, with speed increase, we should provide more resistance to avoid buckling for the safety of the stability of the track. But the higher of the shoulder, more occurrence of the ballast flight. We have to, on the contrary, we have to not increase it, but reduction it. So resulting problem for the future buckling. So my proposal for this, for the Beijing to Zhangjiakou high-speed, the first one, 350 km/h, is use 0. This is the same thing for Italian. Italian 10 years ago, they used shoulder ballast for 300 km/h. Ballast-flight. So they had to follow the rules of Spanish, French, use 0 shoulder ballast. Okay, next one. There is a very famous guy working in UIUC, once working for the SNCF. He said for this high speed, miners also reduce the shoulder ballast. But result, as we all know, result in the lack of the resistance. Next one is support stiffness. Okay, this one. Higher speed ballast bed need well compaction. Very difficult to compact the big size particles. For example, French use 4 times tamping and stabilization, but China will use 8 times. Not only use money, but also damage for the ballast bed. So maybe next week have Alkali invite for a talk for this issue, find an efficient method for the compaction ballast bed. And we also see that maybe in future, for the higher speed, stiff support need increased. How to reach this goal? Next one.
One quick question. How do you get the density of the ballast bed?
We use, we call it a loaded, dynamic loaded train to push it. A train, special train, to push it and to detect. All these parameters, this one is very easy to test, but this one difficult, and much more difficult this one. China is the only country in the world to make the rules for the density. In fact, this density varies with particle density, material density. So in my opinion, stupid. And it's very difficult to test it, to check it. For example, now we use nuclear, radioactive method to test. You know, radioactive method management in China is very big problem in China. In case of, for example, missing, and I can use these small things to, for example, to kill you, to murder you. So nobody, the railway company don't want to use this technology. So we have to find, maybe in the future, find an efficient solution for the density, stiffness, thing test. Next one, measures shall be taken. This translates from our course. Our measures usually relate to polyurethane fixing. This method in other countries used for the reinforcement for the curve or the transition zone. But we use it in not only in transition zone, but also to prevent ballast from flight. And Japan use this method. It might be no good because it needs laboring maintenance. Next one, recent case for sharing. This is a Hefu, okay? Hefu Lab, operated last year. We call it the most beautiful land in China because across the mountains and very, very famous sightseeing. There was once 2 kilometers of slab track due to big settlement because once was an old lake. This is south of China. And we had to remove 2 kilometers of slab track. 80 workers worked 1 month to remove it. And we replaced with ballast track. And the director asked me the solutions. So we use 0 height ballast shoulder flat. And because they are too careful to know for no 0 mistake, so they by labor they pick up small particles, flat particles, because just 2 kilograms, it's okay. But if 200, and there was no ballast flight, the speed is this one. And I should notice that 3 years ago, we have a 350 kilometer per hour test on bridge, 3 times of validation. There is no ballast flight. We use the visual method, mark small particles with color and position, before, after by the camera to test. No ballast flight for the speed of 350 km per hour. This is just to prove that our high-speed train better than lots of the other countries, with better design of the aerodynamics. I could not present the photos because the intelligence belongs to the China Railway Company. All the other money comes from China National Science Foundation. It's okay. This is for the human all the world. But China Railway Company intelligence just belongs to them. And next one, this is my innovation method. Okay, can see. This is polyurethane, soft one. There are millions of polyurethane. This is relatively soft. We just cover the surface, very shallow layer. For example, here, we can design and control the polyurethane strength and just fix ballast particles from dislocation, flight, but also tempt. This technology will be mostly used in our first railway high-speed ballast track from Beijing to Jiaotong, which is for the future Winter Olympic Games. First operation speed is 350 km per hour, but after 1 year, less than 1 year, we change it to 250 km. If we use slab track, we could not change the inclination, but if we use ballast track, we could use it. Another reason why we use ballast track is that we will cross even just less than 200, just even with less than 100 miles, but there is cross the earthquake zone. We have that's why we use ballast track. This is for Winter Olympic Game, political product. At all cost, just make sure no ballast flight. Okay. Next one. Okay, this is contribution and development evolution. Next. Experience comes from several years ago when I did the ballast reinforcement by the polyurethane. We found out that with totally reinforcement by the polyurethane, we found out that 10 times, more than 10 times lateral resistance increasement, more than 12 or 14 times of longitudinal resistance increasement. This is far more than we needed. So my idea occurs to my mind that why not use specific zone, specific position, avoid, for example, here. Along this is the tie. This is polyurethane. We still can use the tamping machine here, tamping. No problem tamping. And no problem for the lifting geometry of the ballast to tie. No problem. And we still could provide excellent enough resistant force to keep the ballast track stability. As we discussed before, with the speed increase without the shoulder, okay, shoulder ballast 0, and even the rib ballast reduced. So this is almost the most efficient method. We use additional polyurethane to the specific depth and position without influence of the tamping and other track maintenance. This is way out. This is way out. And next one, for higher speed, as we mentioned, for example, for the 400 km per hour. Here, less resistance. So we either use the big, heavier, or frame tie to provide enough contact and resistance. Also reduce the dynamic force. For example, longitudinal leather slippers, leather ties, or the external fastener. Fastener has its limitation for reduction for the dynamic. Next one, we use minus 50 two ballast particles. Next one, asphalt layers. Asphalt layers, the very famous professor, Gio. What's the name of the professor? Jerry's research on the asphalt layers. Asphalt layers may be used for the Russia product because this layer could be used to protection the freeze, soil, and also provide less dynamic vibrations. Furthermore, this one can reduce the subgrade work a lot because, I don't know, maybe local soil of the stability not good enough. Next one is just a perspective maybe for the next years, 10 years, cooped. FEM with CFD, so we can investigate when the train pass by, both the dynamic force and the air pressure distribution. The two parameters, both the dynamic air acceleration and the air force. So we can use these values to evaluate the ballast flight possibility. Next one, maybe this is all my presentation. Questions are welcome. Thank you all. Thank you.
We do have time for some questions. I guess I'll start with one then. So what do you think are the most important factors affecting ballast flight?
In fact, should be, in my opinion, should be vibration. Vibration. If we can control the, because when we did the ballast window tunnel test, even the speed of the wind is 30 km per hour, almost relevant to equal to the speed of 350 km per hour. The ballast particles just dislocation, not pick up. If the ballast bed no pick up initial movement, initial momentum, normally the ballast will stay there. Anybody else? So.
What's your projected service life for the polyurethane treatment? Is this going to last 5 years, 10 years, forever?
Okay. Excellent question. Okay, this is based on the protection purpose. For example, for our high-speed railroad, first one, from Beijing to Jiaotong, the local authority just want 1 year duration, 1 year of service time. So it's no problem. The big issue for polyurethane application in the world because of maintenance. Normally, after 1 year or 2 years, there should be tamping. So the time of the service of the polyurethane, no problem at all, but depend on others, tamping work. So my solution is to, the first one solved is just aimed, developed for this Beijing political product. 1 year service time, make sure no ballast-flight. Others, for example, for my partially specific zone could last for very long years because this materials has been tested by the physical and the long-term test, no problem. And this company gave me the research money, and we researched the product oriented from the industry needs, no problem in 10 years. And also, polyurethane could be used for desert lines. Foamed surface just covers the surface layer of the ballast bed in desert lines, and without intrusion of the sand or other pollutions. So we can keep the ballast bed elasticity and, as I said, not depend on subject to the chemical materials surface time, but because of the tamping time. Okay.
Have asphalt emulsions or products of that sort been tried for the same type of application?
Yeah. We try, for example, for our softer polyurethane, we have file cans. The company sent me file. I give a rough estimation how much the value. For example, the maximum for them is 2 megama, and next is 1 MPa. So after that, file cans, we selection which one is flexible and good enough to keep it. For the polyurethane, this is, as I said, millions of cans. You can design the whole stuff very strong, and you can design it for foam, microfoam, lots of foam. There are lots of the valid. For example, in American, they have strong, expanded foam polyurethane, and in China we have soft, expanded foam polyurethane, and we have the no polyurethane foam, no foam polyurethane. This depends on your use and your purpose. We use micro foam to reduce the volume of the polyurethane, reduce the cost. Just this is some skills, chemical engineers, they know the reason. We just list the needs, requirements, see how they have the method to. And another method for me is that, in my opinion, every chemical reaction could be reversed. So maybe after several years of application, we use another additional, for example, materials, spray it on, and dissolve solution, another solution to make it separate. Maybe chemical or physical, hot, cold method to detach it. This depends on the needs, choice, or cost. Okay.
I have 2 quick questions. One is, I think in one of your designs you showed the 50 millimeter, 5 centimeter decrease in the shoulder height, correct? You were suggesting that as one of the 50 millimeters, 5 centimeters. Is that going to cause any lateral stability issues?
If without additional measures, for example, the tie, design heavier or broader or frame, if we reduce, no problem. There will be huge problem. So must be research on how to, with the reduction of the lateral shoulder ballast, we have to keep have to increase the slipper resistance. Right. So that's our work, how to maybe other methods.
Because I know you're trying to minimize ballast flight, but you're compromising maybe the stability, and that should be probably looked into, right?
Compromise.
Yeah, the second question is, I know you talked about shared corridors for France, but actually I know in the southern China with the heavy haul lines, now there's more of a talk about maybe increasing the axle loads in freight transportation, and maybe some of those lines may be seeing passenger. Is there any plan to, have shared corridors in southern China?
Okay, I share with you. China, we have academy, like Jiaotong, our chief engineer of CRC. His name is He Huawu. He get his academic title because his contribution for the slab track. But somebody, maybe the vice chief engineer now, he want to become the next academy. So he should do something creative. One solution is for develop the heavy haul, faster, more than heavy haul track system. Somebody want to suggest use slab track, but nobody dare to shoulder the responsibility. The future solution should be modern heavy haul ballast track. Your collaboration with Central South, they have the research platform, modern ballast track for heavy haul system. And another solution is, for some developing countries, is share corridor, because they don't need too fast speed, but they also build one line, both service for the freight and passenger.
So that was my follow-up question to this. So, because I'm not aware of any place in the world where people are running what I would call true heavy axle loads on the same track that they're running at 300 kilometers per hour. Is that being... They are doing it in Italy? But with...
They run isolated freight train.
But still not what we would call heavy haul. It's not heavy haul.
It's a little bit higher, but not heavy haul like in the States.
You had a question?
Jing, I have a question. So, did you look at the different effects, or the different aerodynamic effects from different trains, to see if that, how does a different kind of train affect the aerodynamic contribution to the displacement of particles?
Something I share with you, I'm working for ballast track, but some others, for example, ICE3, the same train working or running on French lines, there's ballast-flight. But a French train, the same speed, the same line, no ballast-flight. So train streamline is the key factors to reduce the aerodynamic. But there is a limitation. Almost this perfect. ICE streamline aerodynamic is not so good because they just working on slab track, not consider too much for the ballast track. French, it's because totally ballast track, so they have to use all those kinds of measures to protect the train hit by the ballast, like the underneath cover, like the nose, long nose, and even China. There is the influence.
Okay, we've got a couple of questions from online, so I'll try to interpret these. So one question is whether the underfloor design of the train or some kind of whatever ice-phobic coating you're using has been considered in these studies. And then the second question is, do you know or have an opinion about which is more effective in ballast stabilization, epoxy resin based on cryorit, Agritech, or polyurethane?
Okay. The first one, some countries, for example, Italian, the former trains, doesn't consider too much for the underneath design. So they have the problems of the ballast hit the underneath, the cover, and there is a trend and becomes the necessary part of the train design, underneath design. Cover, streamline, reduce the air force, but also protect heating from snow and accumulation of snow. So underneath design should be necessary and incorporate into the train design. The next one is about maybe I don't know, I got the right question. For the stabilization of the ballast bed, this is very, for example, several years ago I provided my knowledge for the Mexico product. The construction company asked me how to reduce how to increase the quality of the ballast compaction. So I just use the YouTube, download the download the French company's method. The Chinese company are excellent. So there is a way out. For stabilization, maybe Professor Arrow maybe he lowers the cost of the soil stabilization. Similar principle. Granular stabilization. Polyurethane is a way out, but not too much dependent. Not dependent too much, because once just like drugs, once addicted to it, you have no others. You shouldn't. And my solution for ballast-flight is comprehensive design, which lots of measures taken, reduce the cost and reduce the risk.
All right. Any other questions for Dr. Jing? Marshall?
I noticed in one of your early slides on one of the ties, I noticed in one of the early slides where you were showing the deterioration of the concrete tie, is that decracking, alkali silica reactivity? What is it? It looked a lot like decracking or ASR to me.
You are meaning the aerodynamic sleeper?
Yeah, your concrete slab, yeah. One of the very first slides you were showing some of the stresses.
This one? No, this one. Okay,
wait. Early on.
Okay, slab track.
Slab track.
Slab track. Slab track.
There you go.
Okay.
Lower left.
Lower
right
left,
there.
this one.
That to me looks like traditional ASR, alkali silica reactivity, or perhaps decracking. So, do they have problems with getting quality concrete?
Okay, during our slab construction or production, in fact, we have a very strict control for the additive to control. Too much additive add in result in the problem in the future, because additive makes the concrete quick, early, good quality, but after several years of but post age will result in problem. So that's why I said it is a pity that at that time we didn't realize too much of this problem. We used too much unknown some can lose control of the additive material. Control the quality, faster strength, early strength, because we need the curing time, but later. So I have about 100 pages of the slab track problems. Water, acid water, all the high-speed train network for the most developed country, the most developed zone of China. Pollution, air, acid water. The acid water pH value is 403, 40, almost like acid. The acid corruption for the concrete, reduce precipitation layer and into the steel bars. Steel bars, once it is rotted, like cancer. So it's a pity that 10 years ago we did not realize this problem seriously. Anyway, concrete is a way of single trip. We could not change it. So now, my solution for them in the future is to use polyurethane coating, protect the water come in, and this polyurethane can not on the surface, not on top of the sleeper, into the surface, prolong the survivability and reduce the corruption. This is way out. But I wrote the letter to the vice chief engineer. The vice chief engineer told me that I have too much other works pressing. This is for the future. That's for the future. But this acid is urgent, like cancer. The early stage, we have the method, remedy method. But the last final stage, give it up. Okay.
All right. Well, it's almost 1:30. If no further questions, all right. I don't see any. Let's give a big applause for an excellent presentation of Dr. Jing, and thank you all for coming.